Welcome everyone. Show of hands, who here knows how to import a Python module without using the import built-in? All right, a decent number. Well, we're gonna finish the talk really quickly because that's how you do it. You just use, or you don't use the import keyword, you use the import built-in. Done. Okay, talk's over. We can all go home. Woo! All right. So really, the title of the talk is a ruse. I'm going to be talking about like the internals of the import library and how it works behind the scenes. And you can take from that how to import without using the imports keyword. But really, we're going to go over what happens behind the scenes when you run from X import Y. And I only have 30 minutes, or 25 because of Q&A, so I'm going to go really fast. So just as a little bit of background information, I work in the San Francisco Bay Area as a developer infrastructure engineer at a company which requested that I don't say who they are. So I work on like package and language versioning, static analysis tools, and linting, and Bazel build systems. And then I have a GitHub account, Bryce Beagle, just my name, and then my Twitter is Ignoremes, where I don't typically post about software engineering stuff. It's really me talking about bicycle and pedestrian infrastructure and hating on cars. So if you're into that kind of thing, go there. First of all, what are modules? At runtime, modules are really just objects, instances of the module type. There's really nothing special about them once they're in your namespace. They can be passed around by reference. They have dunderdicks with their own internal namespaces. You can access attributes on them using the x.y syntax, and those attributes can be either just variables or methods or other classes. So modules can come from py files, and that's how you're typically used to seeing them. You import from a package or a module, and it's really just a source py file on your file system. But they don't have to come from source files. They can come from compiled binaries, like in this case, polars, which is implemented in Rust behind the scenes. It actually, when you import it, it's coming from a shared object file, or on Linux and on Windows, it's going to be a DLL file. Modules can be packages. So all packages are modules, but not all modules are packages. Here we have like the sys built-in. It's just a built-in module. We got a sys, which comes from a py file, like I said before. Click also comes, it's a package here. It's not coming from a click.py. It's coming from an int.py and a click directory, so that's why it's a package. And then poetry is a special kind of package where it's a namespace package where it's kind of implemented across multiple different directories and kind of merged together at runtime, but we're not going to go into that. But there's just a whole bunch of types of modules and a bunch of types of packages, but for the sake of importing, they're all the same. Well, not like the implementation, but like once you are using them, they're all the same. So modules are global singletons. You import it once, you can modify its namespace, and you import it again, and it's going to be modified elsewhere. It's an object that you can access from anywhere as a singleton, basically. So if you've ever done any, modules are also cached. When you import a module once, the next time you import it, it's going to be reused. It's coming from a sys.modules dictionary, and if you pop from the dictionary, you can kind of force it to re-import it the next time you use the import keyword. And then there's inside the importlib is a dedicated reload function, which you should use instead of touching the sys.modules cache. So in summary, modules are just dynamically loaded, highly reusable objects, accessible throughout a code base. They're just objects that you can access easily. And now that we've learned what modules are, we can kind of move on to the more interesting question. Like how does the interpreter find them, and how does it load them into the runtime? Like how are modules? So the steps of importing, sorry, let me make my speaker notes a bit bigger. I'm having to look at my slides more than I should. Okay, what does importing do? First, the package needs to be found, then it needs to be loaded into the interpreter, and then the package or module needs to be bound to the namespace in which it's imported to. So the overall hierarchy is you take your just normal from X import Y, the import keyword is used. That calls the import dunder that I talked about at the very beginning of the presentation. And that invokes a finder object. And that finder is responsible for going to find where the source file is located and then returns what's called a module spec. That module spec is then fed into a loader. That loader then loads the module, and that gets passed back all the way up the chain, and the import keyword is responsible for binding the result to the namespace that imported it, or whichever namespace it's going to be imported into. So if you just use the import keyword, or import built-in, that final step of binding it to the namespace does not happen. You just, the function returns an object, but it's not going to exist, it's not going to be assigned to a variable for you to use. And that's what the keyword is responsible for, among other things. So yeah, as I said, the import keyword calls import, figures out which attribute needs to be retrieved from the thing that's being imported. So if you do like import collections.abc, you need to bind collections and ABC. You need to bind ABC to collections and then collections to the importing namespace. There's just a couple other examples. Okay. Sorry. Okay. So, sorry, I'm really nervous. What was I going to say? All right, as I said, the import built-in is called by the import keyword. It invokes the finders and loaders. It does not bind a result to a variable, and you're not really supposed to use the import import built-in function to import things dynamically. The importlib module has an import module function that you should be using instead, and it manages caches a bit better. It manages there's some invariance that the import machinery relies on, where it expects the keyword it expects some state to be set outside of the import built-in that the import module function does. And so you shouldn't really be using the double underscore import method on your own. You should be using this provided function. So loaders. Loaders are just abstract methods, and there's some that exist in the standard library implemented by default. And all they need to define is a create module and an exec module. Sorry, wait. I skipped a slide. Finders. Okay, so first, to find the module, you need to have a finder object. The finder object needs to implement a find spec method, and that method is called by the import, the double underscore import method, to figure out where to find the package. So it's given the from X import Y path, so it's going to ask for X and it's going to ask for Y. It's like, where can I find X? And if Y is a package, it's going to ask for where to find Y, or a module, it's going to ask where to find Y. So this find spec method on the finder object needs to return a module spec that just declares, here's where I found this, and here's the loader that I'm going to have the interpreter use to load the package, or load the module into the interpreter. So here we have the built-in importer, where you ask to find the spec of sys, and it returns the built-in importer loader, and that loader will then take the spec and bring the sys module it'll load the sys module. Okay, loaders, they need to define two methods, a create module method and an exec module method. The create module method is responsible for creating the module instance object. By default, you don't need to implement this. Most implementations just return none, and then that just tells the import machinery, just do your default thing, make me an empty module and populate it. And then the exec module is actually responsible for taking the file that it found, or the SO, or however it's getting the module, and shoving all the things into its dict attribute. So this is how if it's a source file, it basically execs the file and takes the contents of that file and puts it into the dictionary of the module. And then there's one other keyword, and that's importers. Importers just define, or they implement both the finder and loader abstract base classes. And when the find spec just ends up returning self as a loader, so that the import machinery is just like, okay, use me for both the finder and the loader. And those are how most of the built-in built-in finders and loaders are implemented. Okay, namespace binding. Once the module has been found and loaded, it needs to be bound to the namespace where it's going to be used. So in this case, when we import numpy as MP, the import statement needs to first load the numpy module and then bind the result to an NP variable. So it's not going to be bound to the name of the module. It's going to be bound to the argument provided to the keyword. Note that using the double_ import method does not bind to the namespace. And then if you do import x.y or logging.config, it needs to bind both logging to the outer namespace and then config to the inner namespace. So it's got to do multiple binding operations. Submodules are not implicitly loaded or bound to the namespace. And so in this case, logging has a config submodule, and it doesn't exist in the logging namespace because we didn't ask for it. But other modules can exist in the namespace because they are imported within the file. So when logging is imported, its init.py is executed, and it imports traceback. And so that implicitly gets put into the logging.traceback namespace. That's only because the init.py of logging executed that import. But because logging.py is init module or init file does not import config, it ends up not being in the namespace. So you have to explicitly import, another slide there. You have to explicitly import config to have it accessible. Okay, where are modules? The default place that people refer to when they talk about importing modules and figuring out where they're going to come from is sys.path. And sys.path is used by one of the finders that's in the the sys.path used by one of the finders that exists in the standard library to figure out where to find source files specifically. And so if you look at it, it's got the directories. So my IDE puts some directories in there. It's got the standard library directories. It's got site packages from my distribution. It's got some other things from IDE. It's just that these are all the places that one of the pathfinder will look for source files to import. But there's also sys.metapath, which is a list of finders, or importers, because sometimes they do both loading and finding, a list of finders to figure out where to, it takes the name of the package and then needs to figure out how to, so first the interpreter, or the import method will iterate through sys.metapath, asking each of these finders, hey, can you handle this name of the package? And if one of those finders says, yes, I can handle it, then it's referred to a loader. If it gets to the pathfinder, because the first three cannot deal with it, then the pathfinder object implementation iterates through sys.path and looks for source files. But before it gets that far, it first imports from like a virtual environment finder that's loaded by like PyEnv or virtualenv. But then it goes to the built-in importer. So if you're trying to load sys or math or any of the other built-in packages, they are handled by the built-in importer, and it will never even check sys.path for a package called sys or a package called math. It's handled already by the built-in importer. And then finally, sys.path hooks is also used by the pathfinder finder. It's a place where you register file extensions to be imported or to be found and loaded by specific importers. So in this case, sys.path hooks has a zip importer finder or importer, and then a file finder. So if we go back to the sys.path, you'll notice on line 5 here, there is a 312.zip file path in my sys.path. That file doesn't actually exist on my machine, but the interpreter is set up to check there for a zip file that contains source files. And that is handled by the zip importer, finder, and loader. And then after that, it checks for .py files in the file finder. And this path hooks is actually a list of callables. So in this case, it's a callable class or a function that it checks the file path and then, it checks the file path and then says, yes, I can handle .py files, or yes, I can handle .zip files. Okay, now we're going to go a bit in depth with some examples to go over what I'm talking about here. And they're going to get more and more complicated. So imagine this, we have this package here with an init.py that prints its origin. So the double underscore spec is some magic attribute that's set by the import system. And the origin attribute on that is just where the import machinery found the module to be loaded. So for source file, it's going to be a string just holding a dot, like the path to the .py file. For shared object files, it's going to be a path to the .so file. So that's going to be printed when the file is imported, because remember, when you import a file, it's executed. Then it's also got a class with some attribute on it. So really just two things. It prints at import time, and then it's got some attributes. And I'm going to keep this example around for a couple slides, and then it's going to disappear because I'm going to run out of room. OK, so here we have just a normal directory that I've appended to my sys.path. It contains source files. Because we use the path finder, or because the path finder exists in the sys.meta path, it's going to be checked for a package called, well, it's going to be, this is called what, is what I've named my package. Can't find it first. I append it to the sys.path. Then it can import from it. It prints, hey, I was imported from here at import time. And then I can access some attributes in the class. Nothing special there. That's pretty typical of what you're used to, other than I just manually put it in my path. Then we can import from zip files using the default import machinery because of that zip importer that I talked about earlier. So I put a zip file that contains my module, or my package here, on my sys.path, and then import it. And I can see that the loader for my package was the zip importer. All right, we can do this manually too. We can bypass the zip importer, finder, and loaders, and implement them ourselves. And I understand this is a lot of text and hard to follow. I did my best to cram it onto one slide, but splitting it up probably was worse. All right, so we have a zip finder. It implements find spec, and it's given the full name to the thing that's being imported. So in this case, it's going to be the string what. Then it, well, here's how it's going to be. I'm going to show how it's used first. So I append a zip to my, nope, okay, going back. All right, okay. Find spec takes the string that's going to be imported. Then it checks everything in my sys.path, because this find spec is used. It's. Sorry, wait. I did something wrong here. All right, I have confused myself. Sorry about this. What did I do? OK. Yes, first. OK. Sorry. OK. We make a path hook that refers to the zip finder that I just showed on the other slide. I'm going to go back to it. So we put in the path hook a function that accepts a path and returns, if it can handle it, it returns a zip finder. And I instantiate it with a single instance attribute of path. Then we use, so it's got a class attribute or an instance attribute on line 7. Then, because we've said we can handle this path, we are given the package name to import, and we check, okay, does a what in a .py exist or a what.py exist? And if one of those exists, then we return a spec that refers to the zip loader. There's a bunch of other stuff here that's important, but not for, I'm going to gloss over it because I'm running out of time. OK, so zip loader is returned by the zip finder. That zip loader implements create module and exec module. Create module returns none because it's just going to defer to the default module object creation. And then it populates it by loading the file from the zip file and then execing the contents into the dictionary of the module that we just created. All right, and then so the path hook I talked about before, we append it to sys.pathhooks as a class method, and then we can import from the zip file that exists in sys.path. All right, next we can talk about importing from GitHub repos. So at import time, it's going to go check GitHub. Does this file exist for this package? And then download it and import it. So again, we implement a finder. We register it with a GitHub repository string, and then put it in the sys.meta path. So it checks the full name that's passed into find spec. Does this exist in the GitHub CDN? I have omitted that implementation. Well, yeah, I omitted that from my slide because it was getting too noisy. But it checks, does this file exist on GitHub? And if it does, then it downloads it, puts it into a temp file, and refers to the source. It uses the built-in source file loader because it's just a file on disk, and you can use the default loader that's saying, OK, here I downloaded the file to this downloaded file path. Please load it from there, and then it execs the file into the namespace. All right. So GitHub Finder puts on the sys.meta path. Oh, and you can see that at import time, it prints out the CDN URL for the path. All right, OK. Now, final example, we're going to import from Rust at import time. So in this case, we're going to register a GitHub Rust Finder with a package that I'm saying. So I'm saying for any package named what, check this Git repository for it and try to download it, build the Rust into a Python package, and then try importing it. So we make a find spec. We implement a finder with find spec that clones the repo, not showing the implementation, builds the repo using cargo build, and then once it's built, it uses the extension file loader, also built into the interpreter, and then it tries to load the package from the path to the SO file. And that ends up just working. We can, using some magic. And so here we append it to the meta path. From what import foobar, and you can see it clones it and starts compiling my Rust package at import time. And then we can use the attributes on it and see that the origin of the import, or the module, is libwhat.so that was built from Rust. There's actually an example where this is useful. If you're familiar with PyO3 or Maturin, there's a Maturin import hook where if you're developing Rust bindings, you can, instead of going cargo build, Python run, cargo build, Python run, you can just add the import hook so that it always builds the cargo crate. Okay, the cargo crate at runtime. But you wouldn't really use this in production. It's just a development feature, and you would probably never import from the Git repository. You'd just do the cargo building part. Things I have skipped over: relative imports, submodules and subpackages, namespace packages, dynamic runtime created modules, things that just don't exist anywhere, but you can just create a module from scratch, reloading, and the PYC byte files. I've got some links here to some documentation. This Git repository that contains my source code. If you guys want to look at that, it also has a link to this presentation if you want that. And then at the import hook I talked about, and then the code image tool that I use to generate the screenshots of my code. And then again, my GitHub and my Twitter. And that's it.
So thank you, Bryce. We have some questions here. So going from top to bottom here, first question, is it really possible to invalidate the module cache after the import to enforce that you are re-importing fresh?
Is it possible to validate the cache? I'm not sure.
Do you want to read it?
It's possible to invalidate the module cache. There are a lot of gotchas and invariants that the interpreter has when reloading modules. And there's like, depending on what portion of the interpreter you're using, invalidating it may not be fully, like, let's go back here. Where did I put this? Where did I invalidate it? All right, yeah, so this reload function reloads the module, but it doesn't actually invalidate all the caches. It invalidates that cache. There are other caches that you need to invalidate manually to do this, and it's complicated, and typically you don't want to reload your modules unless you have a very contrived use case for it. So like the finders and loaders that are built into the interpreter have their own caches. and those are not implicitly invalidated by this reload statement. So if you want a true invalidation, you have to do some extra work. Next question.
Okay, the next question is, in what scenarios does it make sense to import modules manually?
If the modules are dynamically generated or they're passed in as like plugins per se, there's some Django use cases where you pass a module name to some Django functions as a string, and then Django is responsible for importing those plugins based on the string path. And so that's going to be doing some dynamic module loading using strings instead of the import keyword. So that's a use case. The other use case is that mature and import hook I mentioned earlier. Next question.
Okay, does the position of the import statements matter?
Well, you need to import it before you use the thing that you're importing. There's a question of, do you put the import statement at the top of the file or in a function? Usually you do it at the top of the file just based on that's precedent, and also because every time you import a function, there is that cache lookup, because you have to check sys.modules, hey, have I seen this before? So if you have a tight loop in a function and you're importing within the function, you probably want to move the import out of the function if you can. But other than that, the position doesn't really matter unless you have some gross thing with your functions that rely on the external state where you need to import one package before another. But again, avoid that. Okay.
Okay, so the next one, how can we ensure tests of production code with broken imports cannot magically pass thanks to caching? For example, import is somewhere in the test suite by chance. This one.
Tests of production code with broken imports cannot magically pass thanks to caching. Well, so one of the very hard problems of software engineering is cache invalidation, and that's just a problem you're going to have to deal with. Does someone have whoever asked that question? Do you have more information about what you're asking? Yes.
Oh, let me go to.
Yeah, it's actually it's very simple to explain, but it's a really strange issue. Is if you've got broken production code because of a simple import statement is broken, you can have tests of that, which if they run in the course of a test suite that somewhere else is importing the module that's not imported properly in the production code, the tests will pass when you run from that particular location. If you run from lower down, the individual test, it will of course fail because of the import. But this is because of this caching, right?
So you're saying that you have multiple tests that import a package, and there's something wrong with the import statement in one of the tests? And
you just have a piece of code where there's a broken import statement.
Okay.
And then you've got a bunch of tests that test a load of stuff, but somewhere in that test suite, that particular import is made correctly.
Okay.
In the tests. So when you run all those tests, yes, just a broken piece of code. It would raise an exception if you ran just that. If you have a unit test for just that function or something, it will fail. But then you run the whole test suite, and because it's imported somewhere else, it will pass. That test will pass. That code will pass. Does that make sense?
So, if I'm understanding correctly, you're saying that depending on the order that the tests are run, if the broken one is executed first, it will fail the test. But if the working one executes first, the other ones pass. I mean, yes. I don't know a context in which you'd have a proper import statement in one place and not another, where it fully resolves in one place. But if you were in that situation where, say, you imported a module, ran your test, and that broke the cache, and then they not just invalidated it but broke it, and then that other import tried to. Sorry, we can talk after, but I'm not. Next question.
Yeah. Oh, so next question. This is going to be the last one. Are .pth files handled by the file finder? Let's start in the sys.path. Should I create metapath fiber to increase efficiency in finding .pth content?
Unfortunately, I know very little about the PTH files, so I can't answer that question.
Okay, should I do another one? Okay, I think we are out of time, but okay, thank you everyone for joining.